machine is deciding on the string W. Okay? So, in other words, by using this machine B, we now have a way to decide whether M accepts or rejects W. Okay? Now that corresponds to the language here. Okay? Now, so we'll build this larger Turing machine that will use B to see whether B's string, we'll use B's language, the language that B recognizes, and we will use this, the Turing machine that does this, to say yes or no whether the language, this language, is empty or not. So we will use this as a part. Now, I hope that's clear. Now, it's definitely getting tougher. Okay. All right. So so that was sort of the essence of the argument, the logical skeleton. Now we get into more of the details of how to construct B, this smaller, if you like, Turing machine, that has from M and W. So perhaps I talk a bit about the reduction. So we're reducing problem A to problem B. What's problem A? Try to find a Turing machine that can decide ATM. Okay? And we're going to reduce that problem to finding a Turing machine B that will decide this language. Okay? Now, what's the language of ATM? Well, the strings in that language, they're of the form, the strings in that language are of the form ordered pair M, W. And in this case, the M is an LBA, comma W. Right? So, A, and we're trying to construct a Turing machine, a bigger one, we could call it S or A, anyway, that uses B. This is the Turing machine for this problem, for this language. Okay? So we'll construct a bigger Turing machine that will use this one as a part. And there's your reduction. So machine A will use machine B. Now machine A, it will be looking at strings that contain information about M and W. Okay, now let's see. Now Sipser makes a comment here. It's not enough just to show that B exists. Right? We have to build it. We have to construct B from M and W. Okay? Because that's what machine A, the larger Turing machine A, that's what it will do. It will. It has to construct B. So we have to show how does a Turing machine, the bigger one, Turing machine A, if you like, or S, whatever you want to call it, how does it get a description of B? Given descriptions of M and W, because go back. Language ATM. How's it defined? It's equal to the set of strings. The strings are of a form, ordered pair, angular brackets. So encoded descriptions of two things, the M, W. The M is the Turing machine you're talking about. A Turing machine, W, and that's a string. And if, with a condition, the property that those strings and the members of the set have to be a member of the set, that condition is that the Turing machine M accepts W, that string, accepts that string. Okay. Right. So ATM, it will have encoded information about M and W. Right. And from this, we have to construct this smaller Turing machine, call it B. And this B, what does it do? It will give an answer to the question, does B, the Turing machine B, does it accept? Is B's language empty or not? So it decides the question: is B's language, L curly brackets of B, the language of B, is that empty? Okay. So how to construct B? And once we've got a construction, we can encode that what B is, and put that into this one's language. Right? So what are the strings in this language here? They'll be of the form Anglo brackets, so an encoding of B, and B is just an LBA, restricted Turing machine, that makes a decision on whether the language of B, whatever B is empty or not. Right? It decides. It accepts that string if the language of B is empty, and rejects otherwise. Okay, it's that Turing machine B decides. Okay. All right. Now we're going to construct B. So that its input is call it X, little x. If that X is an accepting computation history, okay, for M on W. So you put W into M, you get the computation history, and if M accepts W, then you'll have an accepting computation history, a sequence of configurations, right, from C1, C2, to CL, and CL is the final configuration. In other words, the Turing machine halted. This machine halted on that string, and accept the state of that final configuration, CL, is an accept state. Okay. Let's just recalling what I've just said. Okay. All right. Now the computational history itself, that string, that is X. So X needs to be in the form of a computational history. So how are we going to format that? Well, in the following way. We separate the configurations, the configs. Here's the first one, starting configuration. Here's the second one, and the final configuration, okay, before the machine halted. And the information. Now, remember, you can. There's a shorthand way of writing down the configuration. Remember, configuration is three things. You have to give three values. At a given moment in the computation, at a given step, Turing machine works step by step. So at a given step, given moment in the computation, the configuration is defined by three things. A bit of revision again here. The state that the machine's in at that moment, at that step, the position of the head at that step on the tape, and the third thing is the contents of the tape at that moment, at that step. Right? And there's a shorthand way, you may remember, so you write out the contents of the tape. That's pretty easy, with just one symbol per square. And then you put the state, the symbol corresponding to the state, somewhere, with all those tape symbols, say in the middle somewhere, and so you'll see a QI, some state, and you interpret that to mean that the next state, the next square to be read, is the symbol to the right of that Q. Okay, if you go back quite a way and refresh how to write in shorthand form the configuration. Okay, so whatever that is, this you write it here. That's the configuration 1, configuration 2, ... and the final configuration CL, and you separate them with hash signs. Okay, just like that. Okay, so that's the representation we're going to have of a computational history. And if it's an accepting computational history, you'll have a Q in here, your final state, that is an accepting. It'll be Q accept, right? in here somewhere. All right. Now, how does this Turing machine B, this LBA, limited Turing machine B, how does it work? Well, so now we're getting into the mechanics of how. I hope you've followed the logical skeleton already from the previous square. So now we're getting into the nitty-gritty, the details. How to actually build B, or what is this Turing machine LBA B doing? Well, it receives an input X. So now if this X is an accepting computation history, then B will accept it. Right? See, B is supposed to accept it. It is this X, this string going in. If this string is of this form, if it's of this form, and in the final configuration, the state is an accept state. Okay? So if X is an accepting computation, well, history, for M on W, and string W goes into M. Right, well, it's been a rather long session. I'll go straight on in the next one.